Good day, wonderful people. If you clicked on this video, thank you so much. Remember to like, share, and if you haven't already subscribed, please do so. So this is the second most recent video that I've done on electromagnetism, and the topic for today is going to be how do we calculate the magnetic flux. This is a topic if you're in South Africa doing physical sciences, especially CAPS, you do it in your third term at grade 11, right? So let's not waste time. Let's just get straight into it. Okay. So let's begin here. What is magnetic flux? So this is one of the most popular equation that you're gonna come across in terms of the mathematical description of what we refer as to as magnetic flux, right? So here you have that letter magnetic flux, right? It's a Greek letter phi, right? So the circle and the line, you see that line over there, it's almost like you draw a circle, then you draw a line, and that whole thing is equals to B, which is the magnetic field. It's measured in Teslas or T. That's this SI unit. Here is the area. So the area of whatever loop that you're referring to. So your loop can either be a rectangle, a circle, a cylinder. So it's very important for you to know how to calculate an area of rectangle, a circle, a loop, etc., etc. And it's actually measured in meters squared. Just seeing that the screenshot that I took here didn't include the units, but it's fine. Now we have also a cos theta. Very important thing here. I think this is where a lot of people get a bit confused. This theta over here, you need to understand what this theta is, right? And it's measured in degrees. So the theta, let's read that. The theta is actually the angle between the magnetic field, so B, and the normal to the loop of area A. So we need to now understand what we mean when we say the normal, right? And the whole thing, now the magnetic flux is measured in Weber or WB. So now I'm going to explain in more detail this theta so that you understand, right? So let us consider a situation like this. Let us say you have a loop here, a rectangular loop or a square loop. You know, on this side it's the length is L, on this side it is B. From there to there it's B. It means that if I want to find the area, I'll just say it's L times B. So it's very important for you to understand that. And then you see this loop is in the plane, is in this flat plane. I would say it's in the x-axis plane. Now we have this magnetic field from here, starting from here all the way. See there the arrows pointing to this direction. So maybe you have your north pole somewhere here and your south pole somewhere on this side, right? So you'll have your magnetic field lines, they are pointing in this direction. But if you look, my magnetic field lines as well as the loop, they are in the same plane. They are in the same plane, right? But now I have to consider this line here. This line is the normal. It means that it's normal to this area over here. So the angle now between this plane that contains my area or my loop and the normal, remember something is normal, it's perpendicular to the surface. The angle between them is always 90 degrees. I hope this is clear. So that angle now between this, the normal as well as the direction of the magnetic field. So check where the direction of the magnetic field is going. It's going this way, but check your normal to the surface. So normal to the surface or to the loop, it's up, meaning the angle between them is 90 degrees, right? So this is what I've written down here. So the angle between the normal, which is this yellow dotted line, right, and the magnetic field shown here by the magnetic field lines, the arrows pointing to the right, is 90 degrees. Now if you go back to our equation, so we said that magnetic flux equals to the magnetic field, right, the size of the magnetic field, the area. So the area, we'll just use your formula. Let's say it was 2 centimeters by 3 centimeters. So you know it will be 2 times 3. But first remember, or let's say 2 meters, because 2 centimeters, it means that you have to convert. So if it was 2 meters, it was 3 meters, it was just 2 multiplied by 3. Then you will get your area, right? And then you say the cos of theta. But now you recognize that the angle between the field line, the magnetic field, the direction in which the magnetic field is pointing, and the normal to this area or loop of area A is 90. So I can just substitute the 90 degrees there. And if you put this in your calculator, cos of 90 degrees is actually 0. So that would mean that the magnetic field B multiplied by A multiplied by 0 is actually 0. So what is this essentially telling you? It is that there is no magnetic flux if the magnetic field is parallel to the loop, or to the area in which your loop is found. If this is not clear, believe me, when we do calculations, it will become clear. So your loop, your area, your loop or your wire or whatever you want to call it is it's parallel to the magnetic field. And so if that's the case, you won't actually have a change in magnetic flux. To have a change in magnetic flux, your magnetic field actually has to go through the loop. So let's look at an example like that. So here in this case, you see that your magnetic field is from here and it's pointing up, right? See that? So your magnetic field in this case is now also perpendicular to your loop, right? You can try to draw this situation in your book, right? So now you have, there's the normal, right? And also the magnetic field lines. You see the normal and the magnetic field lines are parallel to each other. And in math, you know, when lines are parallel, the angle between them is 0. So the angle between the normal and the magnetic field lines is 0 degrees. So we do the same dance that we did before. We say BA cos theta. In this case, you know that the angle between the normal and the magnetic field is 0. All right, so you substitute in space of theta, you substitute that 0 over there. If you put this whole expression cos of 0 in your calculator, or maybe you know it, the cos of 0 is just 1. So that will say meaning the magnetic flux will equals to B times A. So here we'll substitute the size. Maybe you'll be given in the question that B is 20 T, and your area, you'll be given the dimensions, and then you can calculate it, and then it's just a matter of substituting there. So it's very important to understand what this theta is. It's the angle between the magnetic field and the line normal to your group of wire, right? So let's see. A line perpendicular, normal perpendicular is the same thing. But sometimes you don't have a magnetic field that is parallel or that is just perpendicular, right? Sometimes it's a bit skewed, you know, or diagonal, right? You see this magnetic field moves from here all the way there. And now you check, okay, my normal is still here, the normal, because this is just on top of creating that 90-degree angle between it and this in this wire loop, right? And then you find that the angle between the magnetic field and the normal is just theta. Sometimes maybe it will be 30 degrees or 10 degrees, and then you just substitute it here and calculate, right? I hope that is clear. I genuinely hope that is clear. So now let us look at a few examples. I'm going to do 2 examples, and I'm hoping that through that it will actually make more sense, right? So the first example that we look at, it says that we have a rectangular wire coil with a length of 5 centimeters and a width of 2 centimeters, and is placed perpendicularly in a magnetic field. So there is the keyword there that they already telling. It's placed perpendicularly in a magnetic field that is 20 T or Teslas in size, as in sketch A. So they are telling us that this wire here, initially, it's placed perpendicularly, meaning the normal would be somewhere here. So you see the normal to this loop of wire. Look at it, this loop of wire. So there will be the normal, because your magnetic field is also normal to it. So knowing what we know, you can already tell that in this case there will be a change there will be a magnetic flux, right? And then the coil is then rotated through 90 degrees to the position in sketch B. So if I rotate this wire to 90 degrees, it's now going to be parallel. See, here it was perpendicular to the magnetic field, here it's parallel, right? Because now you'll say, where's my normal? My normal is going to be somewhere line, straight line, maybe straight line from here to there. I'm going to show you this in calculation. And then your magnetic field will be here, and the angle between them will just be 90, right? And I say calculate the change in magnetic flux after rotation. This is very interesting, very straightforward. I want you to be able to calculate the change in magnetic flux before you are able to now actually calculate induced EMF, which we're gonna do in the next video, right? So I hope this example will explain it much better. Thank you. Okay, so this is the question that we are trying to solve, right? So it's just, I want to highlight a few important things. When you're writing, it's also important to highlight. This is going to be important because it talks about the length of this wire here, of that wire coil, and the width here. We're going to use these two dimensions to calculate the area. And then they saying it's placed perpendicularly in a magnetic field. They've given us the value of the magnetic field. They say it's 20 T or Teslas, as shown in this sketch. So essentially, what is that telling us? I want to pick a color. Okay, this is fine. So if you look at this sketch over here, remember the normal, it will be that perpendicular line to your surface that you're interested in. It's going to be perpendicular to whatever plane your surface that you're interested in is in. So the normal in this case is going to be here. Hope I can draw straight. That line, it means, you see, it's perpendicular to this whole entire surface. I hope that is clear. So let me see. So if you have a surface like this one, oh, that's bad. It's very difficult to draw straight lines using this thing. So if you have a straight surface, right, imagine that to be straight. The normal line would just be like this, meaning the angle between the surface here and that normal is going to be your 90 degrees, right? So it's always that perpendicular line to whatever surface you're interested in, right? So now if you look here, the way this whole thing is positioned, just look carefully at it. Something that is perpendicular, the normal line will be here, represented by this small red line, right? But now when you look, you say, okay, what's my theta then? Remember, we've said that the theta is the angle between the normal, right, in this direction, and the magnetic field. And if you look at them, these two lines are parallel, meaning that theta in this situation is just actually 0 degrees, right? So let me write this as theta for A. Now if we move on to the second situation, so if we look at this situation over here and we say the normal, so now actually before we go there, they say now the coil is then rotated through 90 degrees. So here it was perpendicular to the magnetic field, right? But now you see it's parallel to the magnetic field. The thing that has changed in this case is the normal. So that normal line is still going to be right there, but now because your wire is almost like facing up, it's just going to be like this. So that will be your normal line. And now if you look, if you say, okay, what's the angle now? I'm going to use a different color. What's the angle now between the magnetic field lines, right? And the what is it? The normal. You see that theta now at this position. So I'm going to call that theta B. It's going to be 90 degrees, right? So it's going to be 90 degrees. And then calculate the change in magnetic flux. Okay, how do we do that? The first thing you need to know is that, the formula for magnetic flux, this is the formula that I know. I was about to lie. The formula for the magnetic flux, in this case, I would say it's given by this Greek letter phi, equals to the magnetic field, right? The area multiplied by cos of theta, the cosine of the angle theta, right? And when we now say something is a change in magnetic flux, or just say a change in something, that essentially means that you have to consider the after and before and subtract the after and subtract the before from the after. So a change in magnetic flux would then be something like, okay, I'm going to say change in magnetic flux. I would say, okay, it means that it's the magnetic flux, the final magnetic flux, and the final magnetic flux is at B. So I can write the subscript B minus the magnetic flux now at A, or in the beginning, right? And then I can write it out now and say, okay, it means that it's the field at B, the area at B multiplied by the cos theta at B, right? Then minus B, or the magnetic field at A, the area of the wire loop because of course here because of theta at A. But there's a few important things. So you must realize that the magnetic field doesn't change, at least in this case. So the magnetic field at B is the same as the magnetic field at A, which was given, they said it's 20T. So you have 20 Teslas, right? Another important thing, the area at B, because it's still the same wire coil, the area at B is still the same area as the one we in A, right? And we can just calculate it. You see that the shape of your wire coil is a rectangle. They mentioned that it's a rectangular wire. So you can just say the length multiplied by the width W. But before you do that, it's very important for you to understand that you need to convert. So your length is given in in centimeters. So to convert from centimeters to meters, you need to divide by 100. So maybe 5 divided by 100, multiply by 2 for the width, and the whole thing must be divided by 100, right? And it's just a matter of putting this in your calculator and you'll actually find that area. And if you do that, I think your area is going to be 0, 0,001 meters squared. Just always double check your answers, right? Okay, so now that we know what B is, we know what the area is, it means we can now actually calculate. So we'll say, okay, the change in magnetic flux. So this whole equation there, it becomes this. So you have the change. Let me just remove that. So you have the change in magnetic flux. So you say, okay, but the field at the field it's 20T, it's 20. But the area you multiply by 0. You can just put this whole thing in the bracket. Multiply by 0.01. Multiply by 0.01, and the whole thing multiply by cos of. So we said that V, the cos is 90. So if cos of the angle 90. Struggling a little bit to write cos of 90 degrees, right? Minus, right, 20 multiply by 0.01, so 0, 0.001 multiply by cos of. So what's the angle between the normal and the magnetic field lines? At A, it's 0, so it's going to be the cos of 0. So I would say it's very important for you to know, memorize, just know what the cos of 90 is, what's the cos of 0. It will help you in the long run, not just in physics, but also when you're doing mathematics. So if you put this in your calculator, you should end up with an answer of let me see, because remember cos of 90 is going to be 0, so this whole thing is just going to be equals to 0, this expression here, and then you'll have 20, or a negative of 20 multiplied by 0.01, which is going to give us a negative of 0,02. Remember, you must include the unit, so you can write Weber, which is WB. And there you are. You have effectively calculated the change in magnetic flux for that situation. Okay, so I decided to change this question a little bit. Remember, initially your your coil of wire was a rectangular in shape, and now I'm saying imagine if it was just a circle, right? And in that scenario, it's a circle, right? Okay, this is not supposed to be there. And then it has a radius of 100 millimeters. So this part here is not supposed to be there at all, right? So but it has a radius of um it has a radius of 100 millimeters. Okay, let me just stop doing that, it's fine. It has a radius of 100 millimeters, and it's still placed in this magnetic field perpendicularly, the same size as before. You know, I was trying to draw a circle there, and then it's rotated again through 90 degrees to this position here, and then you have to calculate the change in magnetic flux. So I'm going to do this question a bit more quicker than the previous one, as it's more or less the same. The only real difference is going to be this part of the area. So we say, okay, let us try to calculate the area. So we know that the area for both situations, because it's the same circle, same wire, it's going to be the same, right? So that area, if it's a circle, remember the area of a circle is given by pi r squared. R is the radius, and then pi is equals to the value of 3,14 if you round it off to 2 decimal places. This is going to be 3,14 multiply by our radius. Remember, it's important, you must convert. So if you want to convert millimeters to meters, you must divide by 1,000. So it's going to be that 1,000 millimeters there divided by 1,000, and that's just going to give us 1, you know. And then remember to put it in a square. It doesn't matter, 1 squared is just going to be 1, but you can just put this expression in your calculator and you're going to get a value of 3,14, and we know area is measured in meters squared. So it's going to be meters squared, right? So you now have your area. You have B, you know, as a previous question, it's still 20T or 20 Teslas. And we can now actually calculate the change in magnetic flux. So we'll say, okay, the change in magnetic flux is going to be given by the magnetic flux at B when it was rotated minus the magnetic flux at A when it was still perpendicular. Everything stays the same. So we know it's going to be B multiplied by A cos of theta B. Remember, it was perpendicular to the magnetic field. After here, no, at B it was, let me just write this, cos theta B, it was parallel. So to find this B, still like the last time, so you realize that the normal is going to be up there on your circle. The angle between them is 90, that 90-degree angle, meaning theta B is 90 degrees. And then this one, it is the normal is still going to be there, same lines in the same direction as the magnetic field lines. So the angle between the magnetic field lines at A and the normal to the wire loop is 0 degrees because they are parallel. No, this is A there. This is going to be cos theta A. So we know, okay, we have 20. What's our area? Our area is 3,14, so we multiply by 3,14. And then cos multiply by, put this whole thing in a bracket, multiply by cos of, so you said theta B is 90. So it's going to be 90. And by now you should already know that the cos of 90 is 0. Minus, now you have 20, the magnetic field. Our area is still the same, it's 3,14. Multiply by the cosine of the angle 0. So the angle here between the magnetic field lines and the normal. Cos of 0. If you put that whole thing in a bracket, you are going to get a value of 62.8, if I'm not mistaken, but you can always check the answer. Just 68. Magnetic flux is measured in Webers, so you're going to write WB. So before we conclude this video, it's just important for you to understand this. So you see here in this situation, when the magnetic field and whatever respective wire loop are parallel to each other, there is no magnetic flux. Only when the magnetic field goes through the wire loop, then we have a magnetic flux. It's an important thing to understand, because in the next video, that's when we're gonna talk about induced EMF and Faraday's law of electromagnetic induction. So thank you so much for watching.